Hi everyone, welcome to our first little online tutorial lesson thing. I hope that you and your families are staying safe and healthy and that you're being kind to yourself during this super strange time. In terms of schoolwork, I hope that you're just, doing your best that you can. I know that it's not easy and it might be a challenge for most of us to try to do some work at home. So be kind to yourself and just do your best. That's all I can ask of you guys. Um, we're going to do a little lesson today on exceptions to the rules that we've been looking at so far with ionic compounds. So just to kind of refresh, where we left off in break is kind of where we picked up on last week. Hopefully the gizmo helped to kind of review a little bit, and the practice sheet last week for naming and coming up with the chemical formulas of ionic compounds. Hopefully that helped as well. If you haven't had a chance to check out the answers that I posted on Google Classroom, you might want to do that. So that sheet was looking at normal ionic compounds. And yesterday I posted 2 matching sheets that looked at some exceptions to those rules. And the goal was to see if you could kind of figure out, what was different, what was going on, see if you could figure out the rule. If you couldn't, that's totally fine. That's what we're going to be talking about today. If you figured it out, then that's awesome, good for you. But again, that's what we're going to be talking about today. So don't worry if you're not there yet. We're going to start though with a little refresher. I kind of just want to make sure that we're all on the same page with the normal ionic compounds. So you might want to grab a little spare piece of paper or just try this in your head. But let's do a little review on normal ionic compounds before we get started today. So the question 1 here is to name the following ionic compounds. Also, I'm going to be going kind of fast. So just feel free to pause the video at any point. If you need to, write stuff down or hear stuff again, that's totally fine. Just pause the video, go back to whatever part you need to hear again. But we're going to kind of move through things pretty quickly. So again, question 1, name the following ionic compounds. So see if you can come up with the names for these 3. And then question 2 is we're going to find the chemical formula of the ionic compounds using both Lewis dot diagrams and the crisscross method. So going forward, we're really only going to be using the crisscross method. It's the shortcut, but I just kind of wanted to refresh what Lewis dot diagrams look like. So try sodium sulfide and magnesium oxide. So at this point, I would say pause. Try all those questions and then we will take up the answers. Okay, here we go. So the answers for the names of these ionic compounds, remember that we're taking the name of the metal first, followed by the name of the nonmetal, and we're changing the ending of that name to "ide," I-D-E. So the first one would be potassium sulfide. The second one would be calcium nitride, and the third one would be lithium bromide. So that's going from chemical formula to name. Now we're going to go backwards. We're going to go from name to chemical formula. So first we'll do that using our Lewis dot diagrams. So for sodium sulfide, we start by thinking about sodium. It's in group 1, so that means it has 1 valence electron. And then sulfur is in group 16, which means it has 6 valence electrons. Now sodium's going to want to give away that electron to sulfur, like so. And now sodium's happy. Sulfur is not quite happy. It has 7 valence electrons now, but it wants 8. Remember, it wants to be stable. It wants that complete outer shell. So we need to add in another sodium so that it can fill that spot there. So now all of our ions are happy and we can write our chemical formula. So remember these numbers at the bottom tell us how many of each we have. So here we have 2 sodiums, and if there's nothing there, then that means there's invisible 1, so there's 1 sulfur. When we crisscross, we're using the charges. So sodium likes to give away 1 electron, which gives it a charge of +1, and sulfur likes to gain 2 new electrons, 2 negatively charged electrons, so it will have a charge of -2. If we crisscross those numbers, like so, we should end up with the same thing. We get Na2S with a little invisible 1. Magnesium oxide, we've got magnesium, which is in group 2, meaning it has 2 valence electrons, and oxygen, which is also in group 16, just like sulfur, so that also has 6 valence electrons. Magnesium is going to want to give away those 2 electrons to oxygen to fill those spots. And so this one's actually nice and easy. We only need 1 of each, and we end up with our chemical formula, MgO. So to crisscross, let's start with the charges. Magnesium just gave away 2 electrons, so it's going to end up with a charge of +2. Oxygen gained 2 electrons, so it's going to end up with a charge of -2. If we crisscross, we end up with Mg2O2, and you'll notice that doesn't match what we have up here. So remember that you always have to put these numbers into lowest terms. So if we have the same number here, they kind of cancel each other out. They're both going to become 1s, and we'll end up with MgO, which matches up here. And you have to do this. It is wrong if we put Mg2O2 because, as you can see with our picture up here, we only need 1 of each. We don't need 2 of each to make this complete. So we do have to remember to always put things into lowest terms. Okay, good. Hopefully that helped kind of refresh our rules for normal ionic bonds. Now we're going to look at the exceptions to the rule. So again, maybe you figured out the pattern in the matching sheets, maybe you didn't, that's totally fine. This part is going to go along, this part of the lesson goes along with the little note that I posted on Google Classroom. So if you don't have that in front of you, it might be a good idea to grab it. Okay, exception number 1 is called multivalent ions. So basically, so far we've been ignoring this whole middle section of our periodic table. We've really only looked sort of at group 1 and 2 and then over here into our nonmetals. So that's because this whole section is a bit of an exception to our normal ionic compound rules. And the exception, the difference is that each of these metals has 2 different versions of itself. It can become 2 different charges. So that's different from what we're used to, because if we look at group 1 here, all of these elements can only become +1 as their ion. But a lot of these metals in the middle here can become, so if we look at nickel, for example, it can become +2 or +3. It's got 2 different versions. And so we have to be careful, and we have to know which version it is that we're talking about, because our formula will look different depending on which one we're talking about. So, and that's what this word means, multivalent, multiple valent electrons. So we've got multiple different versions, and each version has a different number of valent electrons. And so you don't have to memorize this. This is on the back of the grade 10 periodic table that I posted on Google Classroom. If you haven't looked at that yet, you'll definitely want to do that, because that's going to be the periodic table that we use going forward. It's the same one as the blue sheet that you guys used for the quiz right before March break. So definitely go check that out. On the back of that sheet, you'll see charts that look like this. And so again, you do not have to memorize the multivalent metals and know which charges belong to each. You'll always be able to use this chart. And so these are our multivalent metals here on the left. We've got a list of a whole bunch of different ones. It's going to tell us what different versions each of those elements can become. So copper here can become a +1 ion or a +2 ion. And then it also shows us the Roman numerals that go along with those charges. So Roman numerals tell us which version it is. If we have just a 1, that means we're dealing with positive 1. If we see a 2, that means we're dealing with positive 2. So you may have noticed on the matching sheet that there was these random Roman numerals in there, and that's what that means. It's telling us which version it is that we're talking about. So we'll go through some examples to hopefully make that make a bit more sense. So first we're going to work on going from the chemical formula to the name. So the only difference in naming is that we need to add the charge in as a Roman numeral. So everything else is the same. We're going to still put our metal first. We're going to change the end of our non-metal to "-ide", but we have to add in what charge is on our multivalent metal. So for example, if we have copper and fluorine, you'll see that there's two options of this, there's two different versions of this compound. We have just CuF, or we have CuF2. And that's because we've got different versions of copper. If we go back, we see that we've got copper can be +1 or +2. So we've got to figure out which copper is in each of these compounds so that we can write the proper Roman numeral in the name. So to do this, basically what I like to do is a backwards crisscross. So if we start with the first one here, CuF, remember if there's nothing there, it basically means that there's a little 1 and a little 1. So if we backwards crisscross that, it means that we started with copper +1 and fluorine -1. And this is good, this makes sense. Copper +1 is one of the options on our chart. So to name this, we would say that we have copper 1 fluoride. And you have to add that Roman numeral in to say which version it is that we're talking about. This one over here, if we do the same thing, backwards crisscross, this time we're bringing this 2 up here. So that means we started with copper with +2 as its charge, and fluorine still -1. So this is copper 2 fluoride. So you'll see that we can't just call either of these copper fluoride. We have to make sure we say which version of copper it is that we're talking about. We're going to try another one. So this time we're dealing with iron and oxygen. So if we backwards crisscross, we know that we would have started with iron with +3 as its charge, and oxygen with -2. Oxygen is always -2, so that's good, that makes sense. We want to, one thing I didn't mention before is it's always a good idea to go to your chart and double check that the charge here makes sense. So if you go to that chart on the back of the periodic table and look at iron, we should see +3 as one of the options. If it's not one of the options, then we might need to think a little bit harder about this one. But luckily, +3 is on that list, so we can just name that iron 3 oxide. Now this one over here, we've got Fe and O. Remember, if there's nothing there, it's really an invisible 1. So if we backwards crisscross, we end up with Fe +1 and O -1. Again, go check the chart and see if this is an option. You should see that it's not. Fe, iron cannot become +1. And also, we know that oxygen, which has 6 valence electrons, always is going to be -2. It only needs 2 electrons. So we've got to think a little bit harder about this one. We don't just write iron 1 oxide because there is no such thing as iron 1. Instead, let's think about oxygen that we know is always -2. So what would have iron had to have been to end up with FeO as the chemical formula? We know that it probably had to be something that would cancel out the 2. Let's try iron with a +2. If you go look at your chart, you'll see that that is an option, and that makes sense. So this one is actually iron 2 oxide. So that one's a little bit tricky. You might need to kind of watch that and think through that a couple times. But basically you're trying to look for whatever version of iron would make sense to end up with this formula. Okay, let's go backwards. So now we're going to go from name to chemical formula, and actually this is way easier. We just use our normal crisscross method, but we just have to be careful of which charge it's telling us to use. So for lead 2 oxide, that 2 is telling us that the charge on lead is positive 2. Oxygen is always negative 2. So when those crisscross, we end up with Pb2O2, and when we put that into lowest terms, we end up with PbO. For lead 4 oxide, that 4 in Roman numerals is telling us that the charge on lead is positive 4. Oxygen, again, is always minus 2. And so if we crisscross, we end up with Pb2O4. Always have to put that into lowest terms, so they don't cancel each other out here, but we can go into lower terms. We can divide by 2, so we'll end up with PbO2. And so that's everything for multivalent. Our next exception is called polyatomic ions. So basically polyatomic ions, when we look at this word poly, it means multiple, and atomic, atoms. So we've got multiple atoms together that act as an ion. So we've got basically these little groups of atoms that like to bundle together, and they actually have a charge on them, and so they can bond with other ions to make an ionic compound. So those are going to be found in the middle here. So again, we're on the back of your periodic table. This little middle section has got polyatomic ions. And so if you look at the formulas, you'll see these little groups of ions. So ammonium has nitrogen and hydrogen grouped together. And the charge on this whole group is right up there, is positive 1. Hydroxide has an oxygen and a hydrogen stuck together, and they always stick together, and they have a charge of negative 1. So, and you'll notice the names of them are a little bit weird. So let's look at how we write the formula and the names for these. Also, just a note, you'll never have to draw a Lewis diagram of these. So they're kind of tricky, they're kind of weird, so just know that going forward that that's not something that we have to do. Okay, so we'll go from chemical formula to name to start with. The first thing you should always notice is that if you have more than just 2 elements, you're dealing with a polyatomic. So if we look at this first example here, we've got sodium, we've got chlorine, and we've got oxygen. We've got 3 elements in here. So as soon as there's more than 2, we know that we have a polyatomic in here. And so usually the cation, the metal, is going to be first, and then it's going to be followed by the polyatomic. So in this case, ClO is our polyatomic. And if we go back to our chart and we look for ClO, we can see it right there. So ClO is chlorate. So we're going to use that name instead of, like, we wouldn't say chlorine oxide, we use this name instead. So the name of this ionic compound with a polyatomic in it would be sodium chlorate. So we still have sodium first, and then the name of our polyatomic from our chart. So the next one, we've got Be. So we've got beryllium, we've got nitrogen, and we've got oxygen. We've got 3 elements there. So boom, right away you know that it's not a normal ionic compound. There has to be a polyatomic in here, and you're going to want to go to your chart and find out what the name of NO3 is. So in this case, this would be called beryllium nitrate. So I want you to try these. I want you to pause the video and give these a try. See if you can figure out what the names of these ones are. Okay. So first of all, let's double check that they actually are polyatomics and not normal ionic compounds. I've got sodium, oxygen, and hydrogen. So we've got 3 there. It's a polyatomic for sure. And I'm going to name my cation first and then my polyatomic. So this one would be sodium hydroxide. Same thing here. I've got 1, 2, 3 elements, and so this would be called magnesium. And then I look at my chart to find out what the name of this is, and it's phosphate. So this would be called magnesium phosphate. Okay, let's go backwards. Now we're going to go from name to formula. So this is pretty much the same crisscross as well. We just will sometimes have to use brackets. And so this is something you also might have noticed on the matching sheet is that, and actually if you look at our previous example, that sometimes we've got brackets with another number outside of the brackets. And so that happens when we have polyatomics sometimes. So let's look at the first one, potassium chlorate. So start by writing the symbol for each of these with their charges. So potassium is in group 1, means it has a charge of +1, and then chlorate, if we look at our chart on the back of the periodic table, we see that chlorate is ClO3, and it has a charge of -1 on it. From here, and remember we're treating this ClO3 just like an ion, so we can crisscross the same as we usually do. We're going to cross those charges, and because it's a 1 and a 1, we don't need to write ones, so we end up with KClO3 as our chemical formula. And then for calcium bisulfate, again, let's start with the charges. So calcium is in group 2, meaning it has a charge of +2. Bisulfate, if we look at our chart, we'll see that's HSO4, and it has a charge of -1. So if we crisscross that, that 1 will come down to calcium, and this 2 comes down to HSO4. And so it would be confusing to write HSO4 with a 2 right beside it. So instead, we're going to put it in brackets. And so what this does is this shows us that we have 2 of this entire polyatomic here. So we have 2 HSO4s. And so whenever you crisscross, if there's a number up here that you have to bring down to your polyatomic, you need to put it in brackets and to show a little 2 here. We didn't have to do that here because it was a 1. If that confuses you and you want to put brackets with a little 1 beside it, that's fine. You just don't need to show it. But as soon as there's a number greater than 1, we have to put brackets, and we have to put that little number outside the brackets. Okay, so that's everything today. I know that's kind of long. Hopefully you stuck with me. Those are our 2 exceptions to our ionic compound rules. I'm going to be doing probably a Google Hangout a little later this week. So if you have questions about this, you can join and ask, or if you can't make it, then just send me an email and we can arrange another time. But for now, I'd like you guys to have another look back at those matching sheets that I posted yesterday and see if they make a little bit more sense now. See if you can figure out what matches to what and how you would figure that out. All right, thanks for joining. Have a great day.